Hello everyone, welcome to the first video on the Brain Buffet YouTube channel. If you've ever felt like your textbook is written in a whole different language, or if your lectures are moving way too fast, you're in the right place. Our goal at Brain Buffet is to break down the hardest concepts into very clear steps so that eventually you could be teaching them also. We're going to be kicking off the channel by doing a series on chemistry. We're going to be covering everything from the periodic table to complex reactions. But this is just the beginning of the channel. As the channel grows, we're going to be going to other subjects such as biology and calculus. For this chemistry series, before we start getting into complex reactions, we need to understand the math that's involved in chemistry, because math is a very big part of it. But even though math is a big part, if we understand the basics, then the math won't get too complicated. One very important part of chemistry is unit conversions. We're going to be seeing unit conversions throughout our journey in chemistry, so it's important to understand how to handle these problems. The method we're going to be showing on this channel is dimensional analysis. So as we can see in this diagram, they start off with this many inches, and our end goal is miles. So how did they do this? Well, if we look diagonally, we can see that we have inches up here and also inches diagonally down here. Why did they do this? Well, by putting inches diagonally with inches, we're going to cancel out these units. And then if you look here, we know how many inches are in 1 foot. We know 12 inches are in 1 foot. It's important to know that when two things are stacked up on top of each other in the train tracks method, they're equal to each other. We know 12 inches is equal to 1 foot. And if we look over here, we also know 5,280 feet is equal to 1 mile. And we can see that when we look diagonally, we're crossing off the units. We're crossing off feet. So, now let's go into a practice problem to get a better understanding of how they did this. So we're starting off with 8.5 minutes. So this is the unit we're going to start off with. And our end goal is seconds. So let's just write down what we know. We know that we have 8.5 minutes. And we want to put minutes down here to cancel out the units. So do we know how many seconds are in 1 minute? Yeah, we know 60 seconds is equal to 1 minute. So if we put 1 minute down here, we're going to cancel out these units. And then if we can also put 60 seconds up here, because we know 60 seconds is equal to 1 minute. So now we have our end unit. So now all we have to do is do 8.5 times 60. And that gets us 510 seconds. Let's go down to another practice problem. So this method is not only useful for our normal unit conversions, but we can also use it for other maybe real life situations. So this problem, we're starting off with 24 Pokemon cards, and we're going to use the train track method to find out how many baseball cards this man can trade. Well, let's just write down what we know. We know we have 24 Pokemon cards. Okay, well, if we look at these conversions, we see that 12 Pokemon cards is equal to 6 Yu-Gi-Oh cards. So we can write down Pokemon cards down here to cancel out those units. We know 12 Pokemon cards is equal to 6 Yu-Gi-Oh cards. Now what do we do? Well, we know 2 Yu-Gi-Oh cards is equal to 4 basketball cards. So we can write that down also. We know 2 Yu-Gi-Oh cards is equal to 4 basketball cards. So again, if we're looking here, we notice that when we look diagonally, we're going to cancel out those units. And then when two things are stacked up on top of each other, we know that they're equal. We know 6 Yu-Gi-Oh cards is equal to 12 Pokemon cards, and 4 basketball cards are equal to 2 Yu-Gi-Oh cards. Now, right now, the units that we have, because we're going to cancel out Yu-Gi-Oh cards and cancel out Pokemon cards, is basketball cards. But we want to cancel that out also, right? So we know 16 basketball cards is equal to 8 baseball cards. So now we cancel out all the units that we do. And now we need to grab a calculator. So when you have things like this, what you do is you multiply all of these together, and then you divide that by all of this multiplied together. So you're gonna do the top divided by the bottom. So it's gonna be 24 times 6 times 4 times 8 equals y. And then 12 times 2 times 16 equals x. And our answer is going to be y divided by x. So if we do out the math, we get y is equal 4,608, and we get x is equal to 384. So if we do y divided by x, we get 12 baseball cards. And it's also important to write down the units because some professors or teachers might take off points. Now let's look at dimensional analysis in more of a chemistry point of view. So some units that are very important in chemistry are the metric units. This skill shows us the conversions between different metric units. To read the scale, let's make our base unit grams. And 10 to the 0 is also just equal to 1. So what this scale tells us is that if we have 1 gram is equal to, let's look at the unit milligrams. So as we can see here, milligrams has 10 to the negative 3. So what does this mean? Well, this means that if we have 1 gram is equal to 10 to the 3 milligrams. One very important thing to remember is that everything down here, these are all smaller than a gram, and everything up here is bigger than a gram. So knowing this, we can reason that even though this says 10 to the negative 3, this doesn't mean that 1 gram is equal to 10 to the negative 3 milligrams. It means that 1 milligram is equal to 10 to the negative 3 grams. And we can use this for all of these units. So if you look at micrograms, if you have 1 gram, that's equal to 10 to the 6 micrograms. And 1 microgram is equal to 10 to the negative 6 grams. And then if we look at units bigger than the gram, 1 kilogram is equal to 10 to the 3 grams, and 1 gram is equal to 10 to the negative 3 kilograms. So now let's use this scale to do a practice problem. For right now, we can just look at the scale to get our conversions, but eventually you do want to memorize this because it's really important, and no professors or teachers are going to give you this scale, so it's important to memorize it. So let's do our dimensional analysis and trade tracks method. What do we start off with in this problem? Well, it says a reaction requires 450 milliliters of water. How many liters is that? Well, we know we start off with our unit of milliliters, and that's 450 of them. So 450 milliliters is what we start off with. Now, we know that if we're looking diagonally, we want to cross off milliliters. So how do we do that? Well, let's go back to our scale. This scale, it tells us that there's 10 to the negative 3 liters in 1 milliliter, right? If we think of our base unit as liters. So it says 1 liter is equal to 10 to the 3 milliliters. So we can cross off our units, and now the units that's left is liters, and all we have to do is do 450 divided by 10 to the 3, and that equals 0.45 liters. Let's look at another practice problem. It says a piece of magnesium ribbon is 0.025 kilometers long. How many millimeters is that? So we start off with 0.025 kilometers. and our end goal is millimeters. So first, let's cross off kilometers. Let's go back to the scale. We know if we're gonna make, let's make our base unit meters. So our base unit is meters. And by reading the scale, we can see that there's 10 to the 3 meters in 1 kilometer. So let's write that down. 1 kilometer has 10 to the 3 meters. Now that we have our base unit, let's cross off meters also because we want to end up with millimeters, right? So let's go back to our scale. We have meters and we're looking at millimeters. Well, based on the scale, we know that there's 10 to the 3 millimeters in 1 meter. So if we go down here, we can write that down. We know there's 1 meter and there's 10 to the 3 millimeters in 1 meter. So let's just make sure everything we wrote down is correct. We cross off our units by looking diagonally, and we end off with millimeters, which is good. Now we need to make sure that if there's two things stacked up on top of each other, that they're equal. This is right. 1 kilometer equals 10 to the 3 meters, and 1 meter equals 10 to the 3 millimeters. So now we can multiply across, and then divide them. So 0.025 times 10 to the 3 times 10 to the 3 equals 25,000. Now, when we multiply 1 by 1, that's just 1. So we get 25,000 millimeters is our answer. So now that we can do basic unit conversions using the dimensional analysis method, let's look at dimensional analysis in more of a chemistry point of view. To do this, we should look at this triangle. So we know that the units for mass is just grams. This is just how much something weighs, right? Well, we also have a new term called moles. You might be wondering, well, what is a mole? So if I go to a Dunkin' Donuts and ask for a dozen donuts, what does that mean? Well, we know 1 dozen equals 12, right? Well, we can use the same logic for moles. We can say 1 mole, and this is also known as Avogadro's number. We know 1 mole is equal to 6.022 times 10 to the 23. So the way we think about in a dozen is that 1 dozen is equal to 12, right? We can use that same logic for the mole. We know 1 mole is equal to 6.022 times 10 to the 23. So now let's look at this other term, M. Well, it says here that M is equal to molar mass. What does that mean? Well, that just means grams over moles. So if we look at this triangle, we see that mass divided by moles is equal to molar mass. And that's shown in the units also, grams over moles. And then we know moles times molar mass is equal to mass. And if we look at the units, we know the units for moles is mole, and the units for molar mass is grams per mole. So if I did my dimensional analysis, this would be crossed off, and our end unit is grams. So we can see here that moles times molar mass is grams. Moles times molar mass is mass. And the unit for mass is grams. And then if we had mass and divided by molar mass, we can see here, using our dimensional analysis, that we start off with grams, we want to get moles. We know that there's a certain amount of moles in 1 gram. So we can cross off our units, and our end unit is moles, and that's what we get. So we know mass divided by molar mass is moles, mass divided by moles is molar mass, and moles times molar mass is mass. So that's important to understand. And now that we know what a mole is, we can go in and do some practice problems. So let's look at this practice problems. It says find the molar mass of H2O. For this one, we need to look at the periodic table. When we look at the periodic table, we look at the elements, right? So what element do we want? We want H2O. Well, that's not just one element. That's multiple elements. There's 2 hydrogens and 1 oxygen. So first, let's look at the hydrogen. We know that there's 2 hydrogens. So let's look at the periodic table and go to hydrogen. When we look at the periodic table, we know multiple things by just looking at the element. We know the name of the element, we know the symbol, the atomic weight, and the atomic number. The periodic table also tells us other things, but we'll get into that in future videos. For right now, what we want to look at is the atomic weight, and that's the number on the top right. So if we look at hydrogen, we can see that the atomic weight is 1.008. What the atomic weight shows is the grams over moles of hydrogen. In other words, what the atomic weight shows is the molar mass of hydrogen. So if we scroll up, we can see that the molar mass of hydrogen is 1.008. So, molar mass of hydrogen, molar mass of H equals 1.008. Now, it says that we have two hydrogens. So to find out the molar mass of H2, we just do 2 times 1.008. And that's going to give us 2.016. So now this is the molar mass of H2. Now let's find the molar mass of O. So let's look at the periodic table again. If we go to the periodic table, we have to find the atomic weight of oxygen. And as we can see, that's 15.999. We're just going to round that to 16. So it says the atomic weight of oxygen is 16. And we know that the atomic weight is the same thing as the molar mass. So the molar mass of oxygen equals 16. And how many oxygens do we have? We only have one oxygen. So we're just going to do 1 times 16, and that's equal to 16. So now that we have the molar mass of H2 and O individually, to find the molar mass of them combined, all we have to do is just add them. And that's going to be equal to 18 grams per moles. So that's how you find the molar mass of an element and a compound. To find the molar mass of an element, say we just had to find the molar mass of, let's say, CS. We just go into the periodic table. As we can see, we look for CS. It's right here. And we just look at the atomic weight. It says 132.9. So molar mass of CS is just 132.9 grams per mole. So now let's use what we just learned to do some practice problems involving moles, molar mass, and grams. So this practice problem asks, how many molecules are in 54 grams of H2O? So we know what we're starting off with. We're starting off with 54 grams. So let's write that down. 54.0 grams. So now we want to use dimensional analysis to find out how many molecules are in 54 grams. So that's going to be our end unit. To do this, we want to first cancel out grams, right? Well, how do we do that? What in the problem gives us grams? Well, we know what the molar mass of H2O is, right? And the units for molar mass is grams per mole. So, using that, we can cancel out grams. The molar mass of H2O is 18 grams per mole. So we know there's 18 grams in 1 mole for H2O. So let's write that down. 18 grams in 1 mole of H2O. Now, we want to cancel out mole. How do we do that? Well, we canceled out grams. So now for mole, let's go back and see what the mole is, right? 1 mole is 6.022 times 10 to the 23. And when we say 6.022 times 10 to the 23, there's no specific unit attached after it. It's just like if we talk about a dozen, right? We could have a dozen donuts, a dozen munchkins, a dozen computers. We can have a dozen of anything. So if we have 1 mole of something, that's 6.022 times 10 to the 23 of anything. So we can use that logic for molecules, right? 1 mole of molecules has 6.022 times 10 to the 23. So if we write that down, we have 6.022 times 10 to the 23 molecules. So now we have our units canceled out, and let's just make sure that everything is right. So we have all these units canceled out, and our end goal is molecules, which is what we got. And 1 mole is equal to 18 grams, so this is right. And 1 mole is equal to 18 grams of H2O. And then 1 mole is equal to 6.022 times 10 to the 23 molecules. So using that, we just multiply across here and multiply across here and do x divided by y. So that's x, this is y, and x divided by y equals 1.81 times 10 to the 24 molecules. Let's do one last problem that uses everything we learned in this video to finish our dimensional analysis introduction. So let's look at this problem. It says a tiny crystal of table sugar C12H22O11 has a mass of 0.850 milligrams. How many atoms of carbon are inside that single crystal? Okay, so let's look at what we start off with. We're starting off with 0.850 milligrams, right? So let's write that down. So we know that, let's get this to our base unit, grams. Because once we have grams, we can interconvert from grams to molar mass or grams to moles. So now that we know that there's 0.850 milligrams, let's figure out how many grams that is. We know that there's 10 to the 3 milligrams in 1 gram, right? So let's write that down. 10 to the 3 milligrams in 1 gram. And one thing when we start memorizing this unit conversion table, to make sure that what we're writing down is right, just think about it. If instead I decide to write there's 10 to the 3 grams in 1 milligram, we know this can't be right because a milligram is smaller than a gram. So it wouldn't make sense to say that there's 10 to the 3 grams in 1 milligram, because that would mean that when we're making the number of grams bigger, we should also be making the number of milligrams bigger because milligrams is smaller than the gram. So that's just one thing to keep in the back of your mind, to always check if what you're writing is right. So we converted from milligrams to grams, and we can cross off milligrams. So now our unit is grams. Well, we know that the end unit we want is atoms. So how do we get to that? Well, it tells us what what compound we're working with. We're working with C12H22O11. So to solve this problem, we need to find the molar mass of C12H22O11. Because once we find that, we will know the grams over moles of that, right? We will know that there's a certain amount of grams in 1 mole. So we can cancel out the grams that we have here to get us to atoms. So let's go look at the periodic table. Let's first look at carbon. If we look at carbon, we see that carbon has an atomic weight of 12 right there. So that means that if we have one mole of carbon, that's equal to 12 grams. So 1 mole of carbon is equal to 12 grams. And how many carbon do we have? We have 12 carbons. So we just do 12 carbons is equal to 12 times 12. That's equal to 144 grams per mole. Now let's look at hydrogen. So hydrogen has an atomic weight of 1, right? So we know hydrogen has 1 gram for every mole. And if we look, we see that there's 22 hydrogens. So 22 hydrogens is equal to 22 times 1, which is 22 grams per mole. Now our last element in this compound is oxygen. If we go to the atomic weight of oxygen, we see that oxygen has 16 grams for every mole. So let's write that down. Oxygen has 16 grams for every mole. And how many oxygens do we have? We have 11 oxygens. So 11 oxygens is equal to 11 times 16. And that's equal to 176 grams per mole. So now that we know the atomic weight of 12 carbons, 22 hydrogens, and 11 oxygens, we can add these up to get our final atomic mass per grams per mole for a tiny crystal of table sugar. So let's add these up. 144 grams per mole plus 22 grams per mole plus 176 grams per mole. And that's equal to 342 grams per mole. So now that we know the atomic mass of table sugar, we can use this to cancel out our grams, right? We know that there's 342 grams in 1 mole. So let's write that down. 342 grams. Let's make this red so that we can keep track of our units. In 1 mole. So now that we have moles, we want to get the amount of atoms. So to get this, we can use our Avogadro's number, right? We know that there's 6.022 times 10 to the 23 of something in 1 mole. In this case, we can say atoms. So 1 mole has 6.022 times 10 to the 23 atoms. And now, if we look and keep track of our units, we can see that we canceled out grams and we canceled out moles. And our final unit is atoms. Our final unit is atoms. So now, all we have to do is multiply and divide. We multiply everything on the top and then multiply everything on the bottom. And then if this is equal to x and this is equal to y, we do x divided by y to get our final answer. So 0.850 times 6.022 times 10 to the 23. And then that, we take that, that's our value of x. Now we do 10 to the 3 times 342 times 1. And we take our x and divide that by our y. And our final answer is 1.497 times 10 to the 18 atoms. So, if we look at this problem, we started off with a certain unit, and we used dimensional analysis to get to our other unit of atoms. And to do that, we found the molar mass. We used that molar mass to get and used Avogadro's number to get our final conversion into atoms. So in future videos, we're going to be expanding on our dimensional analysis and going into more complex problems, while also going into more specific chemistry that's involved in the periodic table and looking at specific chemistry of elements. Thank you, and I hope you enjoyed.